okay, goal, yeah, to come up with a formulation that maximizes the margin. Okay. So, how can we do this, right? So, what do I mean by this, right? So, how can we mathematically make this statement precise? We can do it as follows, right? So, we want to maximize, gamma, you want to find a W that maximizes the margin as much as possible, right? So, the parameters of our algorithm are W and gamma, and we want to find a W and gamma such that gamma is as large as possible, but we cannot allow all possible W's. We will only allow W's which linearly separate the data set with gamma margin, right. So, which means that such that W transpose xi into yi is greater than or equal to gamma for all I, right. So, what are we saying here, right? So, we want to maximize the margin as much as possible, that gamma value, such that for your data, the W that this algorithm, this formulation outputs has to have the property that W transpose xi yi is greater than or equal to gamma. That is, all the points are on either side, either on the right side of the line given by the equation W transpose x equal to gamma, or on or left side of the line given by the equation W transpose x equal to minus gamma. That is what this formulation is telling us. So, I think this is a good time to pause and think, is this really specifying exactly what we want, or are we missing something about this formulation? Now, let me tell you what we are missing about this formulation now, and that will give us a slightly different way to think about this. Now, so what we are here saying is that, let us say I have some W, right. So, let us say this algorithm outputs a W, and now why did this algorithm output a W? That W had the largest gamma. What does that mean? That means that W first of all satisfies W transpose xi yi is greater than or equal to gamma for all the data points, which means that let us say gamma was some value 5. So, which means that this is the line set of all x such that W transpose x equals 5, and this is the set of all x such that W transpose x equals minus 5. So, which means that this algorithm is now going to say, well, here is the W which is the answer to this problem, and the gamma corresponding to this W is, let us say, 5, right. So, this is what the algorithm outputs, let us say. Now, this equation is W transpose x equals 5. The moment you tell me that, hey, here is the W and this is the corresponding gamma, now what I can argue is that, look at the corresponding W, which is, let us say 2 times W transpose x equals 2 times 5. If every x on the line satisfies W transpose x equals 5, then every x on the line also satisfies 2 times W transpose x equals 10 naturally, right. So, it is just scaling both sides left and right by 2. So, this is also true. Now, this means that now here is another W which is W dash transpose x equal to 10, where W dash has the property that it linearly separates this data set with margin 10, right. So, with gamma is 10. So, which means that if you had given me W and 5 as the answer and claimed that that is the answer to this problem, now I am saying that that cannot be the answer, because you can scale W by 2 times and then the gamma also scales up, right. So, which means that now you can keep scaling W infinitely such that the gamma can grow up to infinity. So, which means that if I solve only this problem, it is not sufficient, because the issue is that we can scale W arbitrarily. So, this is not going to be a useful formulation, because W can grow arbitrarily. So, we have to ground W. How can we do that? Well, one simple way to do that would be to just say, like how we did in the perceptrons assumption, that we are not going to allow all W's, we are only going to allow W's which have length 1, which means that our modified formulation is going to be maximize over W and gamma such that W transpose Xi into Yi is greater than or equal to gamma, nothing changes so far, but then we are only going to allow W such that norm of W is 1, right. So, which means that I cannot scale W, right. So, the moment I do W to 2W, then the length of W changes. The norm squared kind of becomes 4 times, right. So, because I am scaling W by 2, the norm squared becomes multiplies by 2 squared, which is 4. So, it is no longer going to be 1. So, which means that 2 times W is not going to satisfy this condition, so that we cannot just arbitrarily scale, right. So, this is a possible solution to this problem, right. So, we can try to solve this problem and then we will get some solution, right. So, this is a reasonable formulation to solve this problem, but now I mean, one can definitely solve this problem that and using optimization techniques, and you will get a W and gamma, there is no doubting that. But one can ask if we really have to have these 2 variables in this formulation. There are 2 variables that we are maximizing over, W and gamma, whereas if you really see, right, so you are only searching for W's with length, with unit length, right. So, which means that in 2 dimension, what this means is we are just looking for W's, so we are just looking for W's with length 1, right. So, now if you have a data set, let's take another data set, simple data set, let's say plus 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 minus 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 minus. Now, let's say we are only looking for W's in the unit circle, on the unit circle, maybe this is a W. Now, the moment I fix this W, which means that I am fixing the direction, the length is fixed in that direction, what happens is with respect to this data set, the moment that the direction is fixed, the length is fixed because we are only looking for length 1, the gamma corresponding to this is fixed. The data set will decide what the gamma is. For this W, let us call this W1, the gamma is going to be, what is the equation of this line, right. So, set of all x such that W1 transpose x equals maybe 5, right. So, if it is 5, then 5 is the gamma. So, similarly, I can search for a W in this direction of length 1, which means that this would be my separator, and again the data set will tell me what the gamma is. The gamma is in this case is going to be this, the equation of this line, which is the set of all x such that maybe this is W2 transpose x equals 3, right. So, maybe this is my gamma. So, the gamma is in fact a function of your W. The moment I fix W, the gamma is fixed. Now, what we are doing in the previous formulation is that we are maximizing over both W and gamma, but then gamma is just a function of W. Now, the way we got rid of the problem that W can be scaled arbitrarily is by grounding W, length of W to be 1. The other way to solve the same problem is to say that, well, I am not going to only search for W's which have length 1. I am going to throw that away, right. So, I am going to say that I do not have the condition that norm of W square is equal to 1, but the moment I throw that condition away, I can scale W arbitrarily, right. So, which means to increase gamma. But now, what I am going to say is that I am going to ground gamma. I am going to say that, well, gamma is always going to be equal to some constant. For example, constant is 1, right. So, what does that mean? That means that, I am still going to search in each direction, but now the way it will look, this picture will look is as follows, right. So, this picture for the same data set is going to look like this. The data set is the same, nothing has changed about the data set, it is still the same data set. Now, if I want W1 in this direction, now what I am saying is that, so this W1 has this line as, let us say, set of all x such that W1 transpose x equals 5. This was our earlier W1. Now, this W1 I will not allow in my set of feasible W's. I am only going to allow W's such that the gamma is exactly 1. Now, I can always get a W such that gamma is exactly 1, right. So, if I find a direction which separates my data set positives from the negatives correctly, then I know that I can scale my W1 to make sure that my gamma is always 1. For example, in this case, I can always set W1 divided by 5 transpose x is equal to 1. This is also the equation of the line set of all x such that W1 by 5 transpose x equals 1. Now, I can say that this is my W1 prime, which satisfies W1 prime transpose x equals 1, right. So, in other words, I now have to scale down this W to this point, right. So, in this direction, well, this would be W1 dash, and now with respect to this W1 dash, the same line will have gamma is 1, right. So, which means that the moment I find a direction which separates my positives from the negatives, now I can scale the direction correspondingly such that these lines on which the data, I can push my data, I can push the lines parallel to this, the line passing through origin as much as possible such that it hits the data points on either side. I can always scale my W such that these lines satisfy the equation that W transpose x equals 1, and on the other side W transpose x equals minus 1. Now, because I can do this, now I do not have to worry about gamma. I can simply say that I will always set gamma to be 1. I am only going to be searching for W's such that such a W will give me lines which are parallel to the line passing through origin, but then with gamma equals 1. Now, if the moment I have grounded gamma, now it becomes a question of what am I trying to maximize. Earlier I was trying to maximize gamma. Now, because I am saying that I am only going to search for W's such that gamma is 1, now what am I trying to maximize, right. So, I now have to maximize this, this width, because that is what I am trying to, make it as large as possible. Earlier we were saying that, well, that width, when you fix W as 1, the length of W as 1, well, that width was just gamma is what we were maximizing. Now, the gamma is 1, so this width somehow has to depend on the length. We will see what that is in a minute. But just to complete this argument, right. So, the same thing with respect to W2, right. So, we now, let us say if we start with W2 here, that would give me the light blue separator, this would become my separating, these would become my separating lines. Now, this line, if this had x set of all x such that W2 transpose x equal to 3, now then I have to scale this by a factor of 3 to get W2 dash, right. So, this would be W2 divided by 3 transpose x equals 1. It's the same line, but then the equation is different for a different W. Now, as you can see, right. So, if I have a smaller width, then what I am essentially doing is I am kind of scaling it by lesser, right. So, I started with W1 and W2 with length 1, and then I scaled it correspondingly to make sure that these parallel lines have length have gamma equals 1. Now, the amount I should scale will depend on how wide is this separation essentially. Basically, it depends on gamma. So, basically now this will give me a different width, the blue line will give me a different width, the red line will give me a different width. Now, what we can then say is that we can say our modified formulation as follows. We can say that we want to maximize only over W, the width that W gives with respect to my data set such that W transpose xi into yi is greater than or equal to 1 for all I. This is an equivalent formulation is what I am trying to say, right. So, now as you can notice, there is no gamma, the gamma is gone out of this formulation because we are grounding gamma. But you can also notice that I am not restricting the length of W. What is this saying is that I am going to allow any W which linearly separates my data set with a margin exactly equal to 1, right. So, with this gamma equals 1, but now what I am going to maximize is this width, right. So, this width is the length between these two parallel lines. We have to find what that width is, but then what I am saying is that once we have find that width as a function of W, then all we have to do is that we have to maximize this width. right. So, this is an equivalent formulation, just that we need to now say what is this, what does this width of W mean. The moment we have pinned down what is the formula for the width of W, then we have a clean formulation. So, let's go ahead and try to find out what is the width of W in this case. Now, how can we find the width of W? So, what is width of W? Well, what is the width of W? Well, what are we trying to find out? So, we have some W, I give you some W and I say that, well, this W divides, it classifies my data set such that this is the line where W transpose X equals 1 and this is the line where W transpose X equals minus 1, and now I am asking what is this width, the length between these two parallel lines. How can we find the length between these two parallel lines? Well, you can simply take any point on one of these lines and then ask the question, well, what is the closest point on the other side, right. So, for this point, this would be the closest point, and then the distance between these two closest points is in fact the length between these parallel lines, and this should be independent of which point I take. If I take this point, the closest point on the other line would be this point, and the length would be the same because these are parallel lines. So, I can actually set up a problem as follows, right. So, I will want to find out, minimize over some z, let us say the norm, the distance between x and z squared such that let us call this x, this would be our z, such that W transpose X equals minus 1, that is you start W transpose Z equals minus 1, you start with a Z which has the property that so you start with an X which has the property that W transpose X equal to minus 1, right. So, X satisfies W transpose X equal to minus 1, right. So, this is a property of X. You are looking for Z such that the distance between X and Z is as small as possible, such that W transpose Z equals plus 1, right. So, you want to find a Z on the line W transpose this line, right. So, this line such that W transpose Z equals plus 1, and the distance from X to Z should be as small as possible, but what should X satisfy? X should satisfy W transpose X equals minus 1, right. So, now this is an optimization problem in itself, right. So, to find this width. Now, we can try to solve this optimization problem. I will not really bother solving this exactly, but you can again solve this using something called as the method of Lagrange multipliers. If you are aware of it, you can try it out. We will not do that here in detail. But what you will essentially get is that, I can either solve this or I can do half of this, that does not matter, because whichever, you can either minimize the distance squared or half of the distance squared, does not really matter, the exact point is going to be the same. The solution to this problem though will turn out to be the width of W will be 2 divided by norm W squared. When I say width of W, I am considering this quantity, right. So, the half of the distance squared between these 2 points, right. So, that is what I am trying to minimize, and that quantity happens to be 2 over norm W squared. So, this is basically the solution to this problem. Now, as you can see, as a sanity check, the first thing that you observe is that this value depends only on W and it does not depend on the exact X point that I care about, right. So, because this is just a distance between 2 parallel lines, right. So, the distance between parallel lines should only depend on what decides that parallel lines, and the only thing that decides that parallel lines is W, not this X, right. So, no matter where I took the X, right. So, if I take an X here, this would be my Z. If I take an X here, this would be my Z. If my value between the distance between this X and Z cannot naturally depend on X or Z, right. So, it only has to depend on W, and as a sanity check we observe that this width is in fact 2 over norm W squared. So, which is good, because now we can actually write down the entire formulation that we want, which can be written as follows, right. So, what we want to do now is maximize over W width of W, which is 2 over norm W squared, such that W transpose Xi into Yi is greater than or equal to 1. So, this is our modified formulation now. Now, this is basically telling us that, then if you go back to our previous picture, it is basically telling us that, if you have a large separator, right. So, a separator is large, then the corresponding W will have smaller length, right. So, why is that? Because the width is inversely proportional to the length squared of W, and that is in fact, if you pause and think about this for a second, you will realize why that has to be true, right. So, because if I take a W, if it so turns out that a W that with respect to a data set, a W that gives me the equation of this line as W transpose X equal to 1 and this as W transpose X equal to minus 1 versus the same for the same data set, if I have a different W which gave me a very small width. Now, this guy is W2 transpose X equals 1 set of all X for a W2, right. Now, because the difference is small, right. So, what should happen, right. So, now we can ask the question, how should the length corresponding to the W that induced this should be, right. Because this line has to have the equation that W2 transpose X equals 1. Now, what essentially we are saying is that the length should be inversely proportional to the width, which means that if this width is small, well, why is this width small? Because the length of the W that produced this is actually large. Why is the length of the W that produced it large? Well, because we are grounding gamma to be 1, right. So, on both sides gamma, for both this equation and this equation, the gamma is now grounded to be 1. So, which means that you want set of all X such that W2 transpose X equals 1. If the width is small, if I told you that the width is small, then the length of X should be, so the set of all X that satisfies this are all here, right. So, these guys, the length of these guys are going to be smaller, right. So, because they have to make this value as 1, right. So, which means that if the width is small, then the length of X's are smaller when compared to the X that you would get in the same direction for the one with a larger width. If the length of X is small, but then the right hand side is 1, then the only way you can make the right hand side 1 is if you make the length of W itself large, right. So, here X in any fixed direction, the length of X is small because the width is small, and so to compensate for the smaller X, your W should have longer length, right. So, and so W2 will have a longer length than W. So, basically then what we are essentially asking now is that if you want to maximize the width with respect to a particular direction which linearly separates the data, then it is equivalent to minimizing the length or length squared of that particular W. So, and that is also true, you can just look at this equation and argue why that is true, because you want to maximize 2 divided by norm W squared, which is equivalently you can say that you want to minimize over W half norm W squared such that W transpose Xi into Yi is greater than or equal to 1, right. So, you can either pose this as a maximization problem where you are trying to maximize the width, or you can pose this as a minimization problem where you are trying to minimize the length of W, because the length of W is exactly equivalent to the minimizing the length of W, length squared of W is equivalent to maximizing the width that W gives you with respect to the data set. Okay. So, basically what we have now done so far is the following, just to summarize, right. So, we wanted to find a W such that the W separates our data sets with as high a margin as possible. Now, what we are essentially saying is that, well, it is equivalent to finding a W with as small a length as possible, such that W transpose xi yi is greater than or equal to 1 for all I, right. So, for all I, right. So, this is our first formulation that we have, right. Now, if you solve this problem, so now the question is, okay, so we have set up the problem, right. So, all this that we have discussed so far is to figure out, what is the problem that we want to solve, and we have arrived at the conclusion that this is the problem that we want to solve. Now, the W that comes out of it will have the property that it will separate our data set with, as large a width as possible. Now, if such a W exists, right. So, because if your data set is not linearly separable, then no W will satisfy the constraints that we have put down. So, this algorithm will just say that, well, there is no feasible solution. But if there is a feasible solution, then you will in fact find such a W which with the largest possible width, right. So, so this is the problem that we want to solve, right. So, now we can solve it in different ways. For instance, you can use gradient based approaches, what are called as projected gradient descent based methods, for instance, to solve this problem and so on. We won't really worry so much about the exact algorithm at this point to solve this problem, but what we would be interested in is to understand what insights can we derive from this problem, right. So, right now we have a clean optimization objective constraint optimization problem that we want to solve. Now, what we want to do is understand any other insights that we can draw from this optimization problem. And typically, when you are solving an optimization problem, one way to derive reasonable insights about the problem itself is to derive what is called as a dual problem to the original problem, the primal problem that you would want to solve, which is just another way of looking at the same optimization problem. But typically, that if you look at it in a different way, you might gain some more insights about what is going on, and that might lead us to more stronger algorithms. So, what we are going to do now is to say that, well, here is a problem, here is an optimization problem which you can solve, and then you will get a W which maximizes the width, and we can be happy with that. But then this is only going to solve a problem which is linearly separable. So, it is not clear how to adapt this problem when the data is not linearly separable, or if the data has maybe a quadratic decision boundary and things like that. So, what we are going to ask ourselves is that, can we look at the same problem in a slightly different way and see if that is providing us some more context about this problem. And what we are going to do next is exactly that. We are going to start with this problem and then convert this into a different problem, equivalent different problem, which will provide us very strong insights about the algorithm or about the formulation itself, right. So, and that will be called as the dual problem to this problem, which is what we will start looking at next.